So for a moment of 2, what we want to write an expression that signifies that you're going from 25 up a distance of 16 feet. So this distance of 16 feet is going to be creating a moment with the horizontal load of 25 kips. Okay? So we write down the expression in the range of 8 to 24 feet. We write down negative 25 times x2 minus 8 plus m2. And that's going to be equal to 0. Because we want equilibrium. So, to go more in depth into this, we have negative 25 times parentheses x2 minus 8, because we when we plug in the 8 at x2, we're going to see that there's no moment over here yet. But when we plug in the 24 onto the x2, we plug in 24 minus 8, so we have 16. 16 times negative 25 plus m2. That's going to tell us our moment of 2 at an arbitrary point along this member.
Skip the other row.
Okay, so we get that on, we have this expression, so we have that m2 is equal to negative 25 times x2 minus 8. Okay? Now, for our third cut, we have 0 to 20.
Won't that be negative m2 equals?
Hmm?
Negative 25 times x2 minus 8 plus m2. Isn't that negative m2 equals that?
Oh, positive.
Yeah.
Positive. This is positive over here.
Okay. Go.
So for M3, we have going from 0 to 20 feet from here to here. Okay? So we write down from our first step, we converted our distributed load into 65 kips, and we have our dimension of x3. So we times the 65 times x3 minus this portion over here, which is going to be negative 2.5 times x3 times a half times x3. And we also have this moment from our moment of 2, which is going to be 445. So we write that down into a big expression. So we have that m3 is equal to 65 times x3 minus 445 minus 2.5 times x3 times a half times x3 equal to 0. So we end up with moment of 3 being equal to negative 1.25 x3 squared plus 65 x3 minus 445.
That's for the M3?
Yes, that's for the moment of 3. We have the accumulation of the moment created by this member, the accumulation of the moment created by this portion of this member, and by this other portion at the overhang.
You should write where m1, m2, m3 is. Because right, huh?
So M1, I'm just going to label the signs of the moment. So the M1 is going to be over here, but our M1 is 0. But just for the sake of knowing where it's at, we're going to label them. Our M2 is somewhere over here. Our M3 is somewhere along this member over here. And now we have our final equation, which is in the range of 0 to 8, and that takes place here at the overhang. So we have around 4 over here. So I will be writing this on this part of the board. So from 0 to 8, we have that 2.5 times x4 times x4 divided by 2, which is the lever arm. So we write that down, and for plus m4 equal to 0, and to the m4 we add 2.5 times x4 times x4 divided by 2. And we end up with m4 being equal to negative 2.5 over 2 times x to the 4, times x4, not x to the 4, x4. Okay? And so we have our 4 moment equations for the real frame. Now we go on to our 2 unit load frames. And we have a 10-second break to write this down. Okay. Now we're going to write the expressions for our unit load frame. Okay. So for we will start off with the diagram for unit load frame 2, because that's how it's ordered in my paper. So we start off by writing our first cut. We have this 1 kip load, and we have the moment acting at M1. M1 is from 0 to 8 feet. Okay, so we have moment 1. We have this 1 kip load. It's acting positive, but when we write it down as moment 1, we have negative 1 times x1. This is our x1, by the way. Our length x1. Okay? For M2, we have, this is from range 0 to 8. For M2, we have from range 8 to 24. And we write M2 is equal to negative 1 times x2. Because when we plug in the 8 to the x2, we have that the moment is negative 8. And when we plug in 24 into the x2, we have that the moment is negative 24 at m2. Okay. Now, from 0 to 20, that's our third moment. Oh, and we write our symbol. So this is M2, this is M1. Okay. From 3 we have, M3 is going to be over here. We have our accumulations of moments. no, we have our moment is 24 kips at the fixed, right? So we take advantage of that. So at M3, we have that our moment is just negative 24. It's just the counteraction of the fixed end moment. So from 0 to 20, our moment 3 is negative 24 kips per foot. Because when we do the free body diagram for this member, we have this fixed moment over here, and it's just counteracting it, as I just mentioned a few seconds ago. Okay, now we go to our unit load 1 frame and make our cuts for that. This is our last unit load breakdown. Okay, so in unit load 1, as aforementioned, we have a 1 kip load acting vertical, and we have it being counteracted at the fixed support, and we have a 20 kip per foot couple at the fixed support. Okay, so we make our cuts one more time. At 0 to 8 foot, at 8 to 24. And at M3, which is from 0 to 20. And then we're going to do overhang. So, since we only have this vertical load acting over here, there is no moment being acted over here. At M1, at M2, and at M4. We only have the moment work at moment 3, which is in this portion. Okay? So our moment 1 is 0, our moment 2 is 0, our moment 3 is 20 minus x3, and our moment 4 is 0. Okay? Now we can find our displacement equations for AX and AY. Now we can do our integration. Okay? Now we can do our integration. So we have all of this. Oh! Going back to unit load frame number 2 over here. I forgot to mention that for M4, our moment is 0. And that's from 0 to 8. Okay? So now going back, we have our 2 unit loads frames. This is unit load frame 1. And its cut analysis, and this unit load frame 2, and its cut analysis. Now we can go on and write our displacement equations for reactions AX and AY. Okay? Now we can do the integration work, and this is where it's going to get, all the drama is going to, and suspense is going to happen. Okay? Now we erase this. We take our calculators out, because it's going to get messy. This is where the action and adventure starts. So for displacement at reaction AX, in other words, our horizontal displacement at the horizontal reaction at point A, we use our unit load breakdowns, and we use our real frame breakdowns. So we used in the range of 0 to 20. So we have integration limit 0 to 20. We take our expression from the real frame M3, our expression negative 1.25 x3 plus 65 x3 minus 445, and we times that by the corresponding third cut from unit load frame 2. And at the unit load frame 2, at cut 3, the moment was negative 24. So we multiply, once again, we're multiplying the moment cut 3 from the real frame, which was negative 1.25 x3 squared plus 65 x3 minus 445, times the third moment cut at unit load frame 2, which is negative 24. And we put that over the constant modulus of elasticity times moment of inertia. Okay, and our range of integration is 0 to 20. Okay. Oh, times dx, that's our axis. Now we take our our cut from moment of 2 in the real frame, which went from 8 to 24, from range 8 to 24. We have negative 25x2 plus 200. That's the moments of the real frame at moment 2. Times the corresponding second moment cut from unit load frame 2, which was negative x2 over EI times dx. And for our other two cuts, we see that in unit load frame 2 and unit load frame 1 and real frame 1, real frame 1, they canceled out, so we don't have to account for those. So those two are 0, plus 0, plus 0. And we end up with negative 78,133.33 E over I. Now we move on to our vertical displacement at point A. Again, we start off with our cut at the overhang, and at the overhang moment was 0 for the uniload frame 1, and we times that by negative x1. We put it over EI times dy. That becomes 0. Now we go to our second moment cut. And we have negative 25x2 plus 200 times 0. That 0 comes from the second moment cut at unit load frame 1. So that becomes 0. Plus the third moment cut at the real frame and unit load frame 1. So we have 0 to 20, and we take negative 1.25x3 squared plus 65x3 minus 445 times 20 minus x3 over EI times dx. And now we take our last cut, and we see that it's 0. So what do? We add this all up, and we get that the displacement is negative 19,000 over EI. Okay? Now we multiply our unit load frames by their moments. We square their moments together. Their moments on the x displacement and on the y displacement. So we're going to start off with the multiplication of the cuts of unit load frame 2. And that was the one with the horizontal displacement. So for the first cut, we have range 0 to 24. We have negative x times negative x over EI times dx plus range 0 to 20. We have negative 24 times negative 24 over EI times dx. And we add this up, and we get 60,128 over EI. Now we go to our vertical reaction. Our vertical reaction. We have FYY. We go from 0 to 20. We multiply 20 minus x3 times 20 minus x3 over EI times dx. And all the other ones, when you multiply them by themselves, they end up at 0. So plus 0, plus 0, plus 0. And we end up with 2,666.7 over EI. And now we multiply the x and the y cuts together. So we sort of do a cross multiplication of x and y. So we write fxy. We have 0 to 20. We have negative 24 times 20 minus x3 over EI times dx equal to negative 4,800 over EI. Now we take our equation to now find what the reaction of AY and AX is. And in simple format, the first equation will be delta AX plus AX times FXX plus AY times FXY is equal to 0. That's to obtain the horizontal force of the frame. Now for the vertical force of the frame, we have delta AY plus AY times FYY plus AX times FYX equal to 0. Mind you, FXY is the same as FYX. Okay. So we write it down. Our expression for our answer that we obtained for the delta AX, which was negative 78,133.33 over EI. We plug it into this first equation. We have negative 78,133.33 plus we have our FXX times AX, which is 16,128 over 16,128 times AX plus our AY times FXY, which is negative 4,800 equal to 0. And now for our second equation, we have delta AY plus AY times FYY plus AX FYX equal to 0. For our delta AY, we had the answer being negative 19,000 plus AY times FYY. FYY was 2,666.67 AY plus AX FYX, which is negative 4,800 equal to 0. Now you can plug this into a calculator and you get your values of AX and AY. AX being equal to 15K and AY being equal to 34.13K. So now we have our values of AX and AY. Now, since we have those, we can just go ahead and do, like we already know all of our reactions. So we can from there just take, go on to the next step and do our shear and moment diagrams. The traditional way, which is by making the cuts, etc., 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 and doing the statics. We have to do the statics over again for the frame, which is what we're going to do now that we have all the reactions. Because now that we have all the reactions, we need to refine what are the reactions at the fixed support. So we redraw our original frame, this time we have our reactions at the bottom. We have 34.13K and 15K, and we have 25K. And we have our distributive being 2.5K per foot. So now we can get our fixed reactions, which are for the vertical, 30.87K. For the moment, we have negative 122.4 Ks per foot. And for our normal, or the horizontal, we have 10K. Okay, now we can use conventional methods which have been taught, and we can find our shear diagram and our moment diagram. And I will draw now first the moment diagram. We draw a structure